Students, today we're going to start learning about propositional logic, in particular, how to symbolize propositions, how to create well-formed formulae, or what we call WFF, for propositional logic. This is deduction section. From now on, we're just going to be doing deduction. So our induction, fallacies, definitions, and introduction are over, and this is the second half of the class. So deduction is non-ampliative, and it's about what is necessary given the nature of representational systems, either math or language or thought. So active reflection exercise, create an interpretation for the diagrams below. We've got we got a circle with planes, we got a circle with trains, we got a circle that has food, but also has a circle inside it that has pie. So I want you to create an interpretation for what the diagrams imply logically. There's no right answer necessarily. I'm just trying to get you to look and to conceptualize. Propositional logic translates between informal or ordinary language and formal language at the propositional level. So in informal language, I might have a sentence like horses are mammals and some dogs are not small. And we don't go inside of the sentence. We just represent the sentence as a whole. So we represent horses are mammals as a whole with H. The and is represented with a dot in this system we'll be using, and some dogs are not small. Some dogs are small is represented with S, and the not is represented with a tilde. So I have introduced already two of the logical operators or connectives, which are words or symbols that combine or modify whole propositions, such as and, which we use a dot for, or, which we use a V or a wedge for, and not, which we use a tilde for. Simple sentences are ones that have no operators. So, for example, dog smile is a simple sentence, and we represent that with a simple letter like capital D, because it's a real sentence, we use capital. Compound sentences have at least one operator. Dogs don't smile is compound. It has the negation operator before the D. So it'd be tilde D. Capital letters represent affirmative English sentences. Always remember that. Whenever you're translating, you translate every sentence as affirmative, and then you represent the negation, if there is one, with a tilde. So active learning exercise, you will learn how to test inferences like this. True or false? If not both Cami and Don are tall, Don is not tall, necessarily we can conclude Cami is tall. True or false? True or false? No boats are planes logically implies no planes are boats. By the end of this part of the semester, you'll be able to answer these in rigorous ways that allow you to connect the sentences here. Not both Cami and Don are tall, with Don is not tall and Cami is not tall, so that you can show, not just tell, why you think it is valid or invalid for this, or why you think it is true or false. So a well-formed formula, a WFF, is a grammatically correct expression in that system, in that logical system. So for our system, we're going to use capital letters A, B, C, etc., all the way to Z to represent simple sentences. So if I have a sentence like the oven is free and the turkey is done, I can use capital T for the oven is free and capital O for the turkey is done. Any letter whatsoever. If you want to use it the other way around, because you like the letters representing actual letters in the sentences, then you would have O first and T next. Variables are letters starting with lowercase p, q, r, s, t, u, v, etc., etc. These represent forms of sentences. What this means is they don't represent actual sentences like the oven is free. it represents any possible sentence of a particular form. So if I said any possible conditional, I'd express it P, and then this arrow here, that means then or if then. So if P, then Q, and that is any conditional. So if I'm going to write a conditional, like say a conditional, meaning any conditional, then I'd write it like this. I would not put it with the capitals because they represent real sentences with real claims. A conjunction of two negations, we put it this way, negation, I'm going to use R, and negation S. Again, I've just introduced these symbols now. I've introduced the arrow for if then. These are the connectives, and these create compound sentences. Each system needs to pick how many connectives and what type. And this is what we're going to choose. We're going to use 5 connectives. We're going to use tilde, or the negation sign for not. We use the dot, which is the sign for conjunction or and. We use the wedge, or the V, the disjunction sign for or. We use the arrow for the conditional sign for if then. And we use the double arrow for the biconditional sign if and only if. So here are our basic connectives that we're going to use whenever we see these letters, see these words, or words that mean not, and, or, if then, if and only if. Then we're going to use these symbols to represent the connections between whole propositions. Connectives are either two-place functions, they connect two propositions and stand between them, or they're one-place functions. So here's an example of a two-place function. Ice cream is cold and sweet. So I'm always going to put this in semi-formal, so I'm going to do a step before I do the formal reasoning to make it easier for you to see how exactly everything is formed formally. So here in natural language, we actually put cold and sweet together because it's shorter, it's more efficient. But I'm going to bring them out. So it says ice cream is cold and ice cream is sweet. So I have 2 complete sentences on each side of my and. And then I'm going to put a dot in between them. I'm going to represent ice cream is cold with C, and I'm going to represent ice cream is sweet with S. So C dot S is how I represent ice cream is cold and sweet. That's a two-place function. You can see how the and goes in between the 2 sentences. The other possibility is a one-place function. The only one that's a one-place function is negation. So these operate on the whole of the proposition itself and stands in front of the proposition it works on. In natural language, here's an example. Ice cream is not bitter. When we make it semi-formal, we actually take the it is not outside and put it on the front so that we know to put our tilde in the front. So we'll say it is not the case ice cream is bitter. Or formally in our propositional logic, we'll put negation capital B. Okay? We need sometimes to use parentheses, right? Both open and closed parentheses, and we always use them in pairs. These are what we use to indicate the main operator. The main operator governs the truth value of the sentence, meaning it's going to be when we are calculating the truth values, we calculate the minor truth values first, and by those values, we can figure out the main operator's truth value. So if there's more than one operator, the main operator is usually the one that is outside the parentheses. For example, if I have negation, parentheses, C or H, close parentheses, and this stands for it is not the case that either the caterpillar or you are hungry, then the main operator is at that negation. The negation operates on the or in the sentence. So what is a well-formed formula? Well, here are our rules of sentential logic. And we're going to talk, I want you to look at this as I'm speaking if you can, because it's very hard to understand logic without actually paying attention to what's going up on the board. So the rules of formation and sentential logic for the system are going to be really easy but we're going to put them in metalogical terms. So we're going to use phi and psi for any well-formed formula. So all sentence letters by themselves are well-formed formulas. So rule one, if I have an A or a B or a C or a D by itself, that's a well-formed formula. And if phi is a well-formed formula, then negation phi is a well-formed formula. So I've introduced the potentiality of using negation in the system. Next, if phi and psi are well-formed formulas, then phi and psi together with the dot, phi or psi together, phi then psi, or phi if and only if psi are well-formed formulas too. And rule 4, nothing else is a well-formed formula. So that closes out all and only what we'll be using when we represent. So examples of well-formed formula, the negation parentheses A and D in parentheses, negation A. This may bother you at first when you see negations on negations, but if a sentence has a double negation, that would be the correct way to translate it. M if and only if M. Not well formed, K, negation M. Here, negation cannot work as a something that goes in between two. It's not a two-place predicate. J, or if then F. In this case, you can't have competing connectives. M, N beside each other. These lack a connective and therefore don't make sense. Or A, or F, and Z with no parentheses. In this case, we don't know if A or F is together or F and Z is together. That would indicate whether the or the and is the main operator. And there would be very different meanings in the sentences without clarity. So I want you to go through and pick out which of these. I'm not going to read these out loud. These are completely necessary for you to look at and read yourself. Okay, but I want you to figure out if these are well-formed formula. Please pause and do this. Same for this one. I'm not going to read this out loud because we're just saying like mumbo jumbo. This in case, I need you to do this on the board for yourself as well. Which of these is the main operator for each of these sentences? All of these are well-formed formulae. You need to pick out which is the main operator. Remember, it's the one that is outside the parentheses is one way to put it, unless sometimes negations cause trouble. So look for negations that operate as main operators as well. That's a hint. Finally, which is main operator for these sentences? This is more complicated, so spend your time. If you need to, you can draw these out. You can print out the PDFs from the course, and you can draw these out. And the way that I mean draw them out is I will connect the parentheses together to make it more clear what the main operator is. So how to symbolize sentences? Well, each simple sentence is represented by a capital letter. You identify first how many different sentences there are in that full sentence. So any different sentence must use a different letter. Then you identify how many repetitions of the same sentence there are. For each capital letter must be the same for the same sentence. This follows the law of identity. For all sentences, P equals P. So every sentence is equal to itself. So if I write A blinks and then I use A for that, and then later on A blink comes up in the text, then I have to use A again. Sentences must be well-formed formulae. I want you to try to translate in 2 steps, go from natural language to semi-formal, then from semi-formal to formal. So here's an example of this. If you want to talk to a hiker, Jaden and Frida are hikers. For the semi-formal, before we put it into formal, I'm going to make it clear what the 3 propositions are. So this is how the semi-formal will go. If you want to talk to a hiker, then Jaden is a hiker and Frida is a hiker. Then formally, that would go T, arrow, begin parentheses, J, dot, F, in parentheses. Next, make sure the main operator is clearly indicated by the placement of the parentheses and or operators. Remember that the logical order may not match the grammatical order. For example, if in informal language I say Herb goes if Martin stays, I'm going to switch that first in semi-formal to if Martin stays, then Herb goes. And that'll make it easier for me to recognize the form that Martin comes first, then Herb, because the if represents the antecedent, and the antecedent here is Martin stays. Antecedent just means what follows the if. For grouping, where to put parentheses to show what is the main operator, this is indicated by words that sometimes indicate begin parentheses, words like both for begin conjunction, either for begin disjunction, or neither, which means not either or. So here's an example. Either both Cash starts the car and Finn scrapes the ice off the car, or the twins will have to pay for an Uber. In this case, the either or and the both give us the begin parentheses there for Cash and Finn together, and the or for the twins will have to pay for the Uber. Punctuation also may indicate main operators. Look for the semicolon, which means and. Also look for the comma placements. You can look also for compounding within a sentence, which determines grouping. If it's in a subject phrase, for example, Quinn and Janae graduated, or Clay will. In this case, we go Quinn graduated and Janae graduated, or Clay will graduate. And then we have the parentheses around the Quinn and Janae, because Quinn and Janae are compounded together in the subject phrase. In the predicate phrase, we can also compound. For example, if she got on stage and either crooned or lip synced, then she karaoke'd. In this case, we would have to say she crooned, she lip synced, she karaoke'd. In each case, right, we would have this phrase, parentheses S and parentheses C or L, and parentheses, then K. And that is following the suggestion of the comma as well. Pay attention. Pause one sec. Okay, pay attention to negations and always represent them. Sometimes they operate on individual sentences. For example, Frida or Darren is not a donor. So that means either Frida is not a donor or Darren is not a donor. Sometimes it operates on whole propositions, like neither Frida nor Darren are donors. That means it is not the case either Frida is a donor or Darren is a donor. In this case, the negation goes outside the parentheses. Then you have F or D together in parentheses. Sometimes negations work on other negations. You can have negation, 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 Q. That's a well-formed formula. So here we go. Practice your first translations. The caterpillar is not hungry. You are hungry and we'll make you pizza. If we'll make you pizza, then we should heat the oven. Either the caterpillar is hungry or we should not heat the oven. You are hungry if and only if we should heat the oven. If you are hungry, then you're not hungry. Okay? Now we're going to do a little detour through Boole. George Boole was interested in the fundamental laws of thought and language. And the way he thinks about language, I think, will help you understand how logic works more generally. So Boole held that a sign or a symbol is just an arbitrary mark, has a fixed, mutually agreed upon interpretation, and obeys laws of representation, meaning logic or thought. Now let's go through each one of those a little bit more closely. First, it's arbitrary. Okay, a sign just stands in to indicate something, some idea or fact. Any agreed upon symbol would work, be it a word, a shape, a sound, or even a letter. Because Boole notices this, he thinks that there can be something to do with language he gives the idea of Roman civitas and English state. Those are different mouth sounds, but he points out that any mouth sound or word or even a letter could be used to represent the same conception of what we use the word state for. So he's thinking about categories here, but we're going to try to apply this to propositional logic. So he says, look, we can use X to mean white things and Y to mean sheep. So XY would be the set of white sheep. So now, active learning exercise, I want you to think. If Z stands for horned things, and X equals white things, and Y equals sheep, which of these would be the correct interpretation of ZXY? A, horned white thing, B, white sheep, or C, horned white sheep? Okay, now we're going to focus on fixed interpretation. For relative phrases, a fixed interpretation is required for clarity. So we've talked a lot about ambiguity and problems with ambiguity and clarity. A fixed interpretation is required for clarity when phrases are ambiguous. So if you and I are in a rational discussion, okay, and you say something, I don't understand what you mean by that, it's my job to ask you what you mean by that, and not to just assume that it's being interpreted one way versus another possible way, especially if they're equally possible ways. Thus, if we have something like, and this is his example, Boole's example, Y's, and we have X for Y's, and we have Y for counselor, we have to define if X, Y together means Y's as a counselor or Y's and a counselor, okay? So what informal fallacies result from ambiguity? Since one can arrange the order of adjectives and nouns without a loss of meaning, for example, rivers that are estuaries and estuaries that are rivers, Boole concludes that now these inverted forms are not simply the fruits of a poetic license, they are the natural expressions of a freedom sanctioned by the intimate laws of thought. Okay, so let's go over that a little bit. If we take an adjective, we can just rearrange how the adjectives are. Okay, and if we have nouns related to other nouns, we can also just rearrange them. So his example, rivers that are estuaries, estuaries that are rivers, we could also say sheep that are white or white sheep that have horns. We can rearrange these qualities that we are attaching to the group with variation, and it makes no difference as to the truth of the expression. So which of the following mathematical law is most similar to how adjectives work? A, x minus x equals 0. B, x divided by x equals 0. Or C, xy equals yx. Furthermore, lost it. Notice how repetition in language works. So he argues that if one says good in relation to any subject, is the same as just saying good. The extra good does no additional work on the truth of that quality. Okay? So this leads him to think that in language, this is sort of analogous to what we do with numbers. It's sort of like P times P equals P, or P squared equals P. So if he's right, I want you to solve mathematically for P. So which number or numbers work for that equation? Okay, if you haven't solved it yet, I'm going to give you the answer, so pause it for you to solve it. Otherwise, I'll say the only numbers that work for that are 1 and 0. So he discovers, and this is Boolean numbers 1 and 0, he discovered that this is the base for language's construction in its self-replication. So pretend you are looking at a set of objects. For column 1, this indicates if a thing is a vegetable or not. Column 3 indicates whether it is yellow or not. Okay? So pick the best interpretation of and and using the Boolean values of 1 equals true and 0 equals false. Fill in the columns representing the connective. Okay, so we'll do this together for this one. Remember, the only numbers we have are 1 and 0. So the highest you can go is 1, and the lowest you can go is 0. Okay, so first we have, let me see if I can get, let me pause this for a sec. Okay, so we're going to do the first one together, and then I'm going to have you do the second one, which will be or. So here we go. So 1 and it is a vegetable and it is yellow. Okay, so in this case, 1 and 1 together is 1. Okay, so how about this one? It is a vegetable, but it's not yellow. Is it true that it is a vegetable and yellow? The answer is no, that's not true. So we put false there, not and for that. It is not a vegetable, but it is yellow. We'd have to say not and for that as well, because it's not a vegetable. So it is a vegetable and it's yellow is false. Finally, it is not a vegetable and it is not yellow, gives us a big old 0. And we have our Boolean table here, and the idea here is that this is only true for and in the case where it is true both for the vegetable and for the yellow. Okay. So this one I wanted you to do first by yourself. Pick the best interpretation of or using the Boolean values of true and false. Okay. Fill in the column representing a connective. Remember again that the limit is 1, for that's the highest you can go. What mathematical operation is and which one is or? Okay, so let's do the or together. Together we get 1 or 1. So it is a vegetable is true, or it is yellow is true. So we get 1. It is a vegetable is true, or it's yellow. Well, it is a vegetable, so we get 1. It is a vegetable not true, but it is yellow, so it's either a vegetable or yellow true. And finally, neither is the case, so this is 0 at the bottom. Okay, so for the and, remember it went, I'm going to write this here if I can, and went 1, 0, 0, 0. That's my 1. And so there we go. Clean that up. That's not very, very clean. But now I want you to think about what mathematical operation is analogous to and on this board. Okay. So what is it? 1 minus 1 equals 1? Is it 1 plus 1 equals 1? Remember, this limit case is 1, so the highest you can go for adding is 1. Is it 1 times 1 equals 1? Is it 1 divided by 1 equals 1? So try all the different ones and see which ones are for and or. Okay, so for the and, let's do or first. Okay, so here we go. 1 plus 1, limit case becomes 1. 1 plus 0, limit equals 1. 0 plus 1 equals 1. 0 plus 0 equals 0. So and is plus. Sorry, or is plus. And on the other hand is times. 1 times 1 equals 1. 1 times 0 equals 0. 0 times 1 equals 0. And 0 times 0 equals 0. So and is similar to multiplication. And again, he's not saying it's exactly the same, but he's saying it's analogous in these situations. So you have shown how Boole conceptualized his what we end up using it for is for propositional logic. Oh, I didn't erase my things. Hold on 1 second. Let me erase. So the forms of sentences, these have variables, and they represent any undetermined sentence. So for example, a conjunction of a sentence in its own negation would be P and not P. And the reason we use P twice is because it says and its own, meaning the sentence. So when it refers to itself, then we have to use the same letter when we represent it. For this one, a biconditional two negations does not say these negations are related. So we would use Q and R here. And because they're both negations, we put the negations on each of the letters. So try this yourself. Use the most precise representation. Use variables to create the most precise representation of the form of the sentence below. The same proposition on each side and the negation of a disjunction. I'm going to leave off here with your truth table, your matrices, which are 2D grids in propositional logic, which will represent the truth values for each of the defined connectives. Okay, so when you're going to be spending time next module memorizing this, so I just want to give you a preview of this. Okay, that's what we did this week for this lecture. We actually have a second lecture, I believe. If you are in my 7-week class, then we have a second lecture, which continues on this theme about propositional logic.